Welcome back to Lesson 5 quiz, and I believe we left off on number 9. And it is asking, where is T-beam action in a two-span reinforced concrete beam most effective? And let's look at a T-beam. Whoops. Here's your T-beam. This is the same type of deal with a... That's not a good looking T-beam. Let's try that again. But it's the same, I would think that T-beam's kind of the same as composite beam. You'll have some stuff up here, and this is usually a slab. It's the way I like to think of it. And it doesn't necessarily have to be, but this will be your effective slab width. Let me think, what do we do? Sometimes you do S, or sometimes it's like L effective, EFF. It's the effective slab width, and I think they talked a little bit about it in the study guide. But for instance, you might not actually get to use all that slab. So for instance, let's say you have a repetitive section here, and you only get to use this much of the slab as your effective slab. You can't count on this part of the slab. I hope that makes sense. So anyways, there is your T section, which, if you're thinking about it, this is a real good section for what? And I would say this is a good section for positive moment, because this, your compressive section, hopefully, sorry about that, your I can't draw a straight line to save my life here. Your distance A is your compressive block. Hopefully it's within this slab, this T section, and that's what the T action is. It says so we want to keep to get that T action. If it's larger, if A is larger than what is this? The thickness of the slab. If you get down into here, then it gets nasty, and you have to run some different equations. So you want to keep it in. You have to do some other different checks and whatnot. So you want to keep the compression block in the flange. I hope that makes sense. That's the dimension A. All right. So anyways, it's asking us, where's a T-beam action in a two-span reinforced concrete beam most effective? So let's draw a quick two-span, and as I said earlier, that this works better in tension, because if you flip it around and your compression block is down here, then you're going to have a lot of reinforcing up here, but not as much compression, concrete for compression. So we really want, this is better in when you have a positive moment as compared to a negative moment. So it should be when we have a positive moment. Now looking at this, your moment diagram should look something like that, assuming it's a equivalent distributed load. Yeah, so you're going to have negative moment right around here, and then you're going to have positive moment the rest of your beams. And let's see what we have. Over the middle support, A, I would say definitely not, because that's where you're going to have negative reinforcing is going to help you out. So in other words, your compressive block will be down here. It will be compressing. I hope that makes sense to you. Because, for instance, let's say you have this type of situation, and you push down right here, and you push down right here, what you're going to get is this type of situation. And hopefully you can see that it's going to bend. It's going to be tension on top and compression on bottom. And then over here it's going to be tension on bottom, compression on top, tension on bottom. So you're going to have tension on top and compression on bottom, and compression on bottom you only have this much width as compared to your width on top is like 3 times as big. So you want to use that compression block if you can in the slab. All right. So where the moment is maximum? Well, I would say if that said where the positive moment is maximum, I would agree with that. It would be good because that's going to give you, the more compression block you have, the better it's going to resist moment. But it doesn't really specify, so that's a maybe. And let's go to C. At the points of inflection. The points of inflection are when it, right here, where it turns from negative to positive, and that, as far as I know, I can't think of any reason why a T-beam action would help that at all. So I'm going to say no to number C, or letter C, sorry. And then D, between the supports. Between the supports. So here's support, and here's a support, and it says between them. So that could be anywhere. Not over the support. I guess you could say if it's over the support, that's negative moment, and that would be between the. So that's not 100% clear, and I never like these thinking questions because they're never 100% clear. But D, either D or B, and maybe between the supports as compared to over the supports. I would say probably D would be your best answer, with B coming in as a close second. Let's see what they get. They say the correct answer in the study guide is D, which is what I said probably would be your best answer. So number 9 is D, and let's move on. All right, moving on to 10. It says select the correct statements. Number 1, compressive reinforcement is used when the concrete section is inadequate to resist the moment. Yes, that's when I don't think we've talked about this before. But compressive, for instance, let's say you have a lot of steel and you have a little bit up here. When the concrete section is inadequate to resist the moment, if you have a lot of steel right here, it could really, not necessarily a lot, but this reinforcing up here will help. It will actually act in compression as well. It's not just in tension. So you can use it in compression. So I would say 1 is okay. If you have a section that is inadequate, if it's inadequate to resist a moment, you can add steel up here, and you can make steel down here. And once again, we've kind of brushed over concrete design. Sometimes if you have a heck of a lot of steel, you'll want to have a little bit of compressive reinforcing. So let's say yes to 1. Number 2, compressive reinforcement. So hold on, let me write this real quick. So 1. Compressive reinforcement in a reinforced concrete beam reduces the beam's long-term deflection. And I would say that is correct, because compressive reinforcement in a reinforced concrete beam does reduce the beam's long-term deflection. Let's go to number 3. Compressive reinforcement reduces the possibility of sudden failure. And that is also yes, and I think we've talked about this in past videos, so hold on, that's 1, 2, and 3. And the reason being is this steel will yield. When you make concrete and concrete reinforcing, and I don't think we've talked about this, or they talk about this in the study guide, you want to do something there's 2 types of failure, and I don't want to make this too confusing, but we'll call it sudden failure or catastrophic failure, or more of a gentle failure, if you will, or a yielding failure. And let's say when this starts to deflect and it gives, and let's say this is in positive moment, it could be either, but positive moment, this is going to be in compression, and then tension in the bottom flange, or the bottom half or whatnot. So this concrete up here is going to crush, and down here this steel is going to yield, I guess, if it starts again. But when this steel starts to yield, I don't remember if you remember our old yield curve here, is it goes up. This is the elastic region. That means if you unload it, this is stress, and this is strain. But if you let's say you stress it up, so you're stressing it, and it's stretching a little bit, it's yielding. I mean, it's not yielding, it's straining, it's deflecting a little bit, let's call it. And then when you take away the stress, it will go back to here, and that's the elastic region. And that's where you get Fy. And hopefully this is starting to make more sense now. I know when we originally went over this, it may have been a little over somebody's head. But once it gets past this, it'll kind of peak over. And then, without increasing the stress, it'll start to just get longer and longer. It'll deform. And then all of a sudden, and this is actually goes way out here, so steel will deflect. This is steel. This is the stress strain curve. And then it actually does something called strain hardening. So when this fails, it will actually, what you want it to do is you want it to start deflecting a little bit so somebody can say, hey, something's wrong. So you want the steel to yield before this concrete crushes. Because once that concrete crushes, it pretty much allows for zero zero stress. So it's not going to resist anything. So if this concrete gives or yields before this steel yields, then it'll be a catastrophic failure. But then if you want the steel to yield first, and it'll start deflecting, and the concrete will still be good, but once it gets to a point, it'll hit here because you didn't increase the stress at all. It'll get to a point, and then it'll start strain hardening, and it'll stop. It'll stop that yield. It'll stop that deflection once you get that strain hardening down, or you reduce the load. But somebody will notice, hey, because remember, once you get past that yield spot, once you let go of that stress, it comes down like this. So you'll still have that deflection. You'll still have that deformation. So it'll show that, but it won't. Notice that the person standing up here did not fall and die. All right. So that was compressive reinforcement reduces the possibility of sudden failure. And I would say yes on that, because it's like steel's intention is the same as in compression, and it will not. It's not going to crush like the concrete. So it will actually start to deflect first. All right, number 4, the cross-sectional area of compressive reinforcement is usually less than that of the tensile reinforcement. Now that's correct, because your tensile reinforcement is what you use as the moment couple. It's completely tension. I'm maybe not describing that the best, but it's your only thing. In compression, you also have the concrete to work, but in tension, you only have the steel, so you're going to need more steel. I hope that makes sense. And then number 5, so we've said yes to all of them. And then number 5, it says compressive reinforcement is used where shear stresses are excessive. And that is incorrect. I have never done that. When you have shear stresses, you want to put in some shear reinforcement, which will be stirrups. So you'll have these are your longitudinal reinforcing, top and bottom. Then you'll have these stirrups like so. And they can usually you'll have the end reinforcing, we'll have a few more. Let's say they're at every, 3 inches, and it goes to every 6 inches a few, and then maybe it goes to 18 or 9. It kind of depends on what you're doing. And that's your stirrups and your stirrups. Here's a cross section. Actually, we have a cross section where it will look like this. And if you do have compressive reinforcing, it will. These bars want to buckle out. They want to buckle just like any other column will buckle when you compress them, because they're very, very, very. KL over R of those things is ridiculously high because they're extremely thin. The radius of gyration is next to nothing. So you need to have those stirrups to help them from buckling. But you'll usually have stirrups anyways for shear on it when you're using beams. All right, so the answer is A, 1, 2, 3, and 4. And that is the end of the Lesson 5 quiz. Thank you, and I'll see you in Lesson 6.